Hello everyone, here's the next problem. So this problem is asking to find all the unknown nodal voltage and current Ix, which is the current through this 2 ohm resistor. So as usual, so using nodal, before you apply the nodal analysis, first you have to pick the reference ground, reference voltage, and usually this is the good choice of ground, right? Reference voltage, and we'll be measuring all the unknown voltages, nodal voltages, reference to this 0 volt. This is our reference voltage, ground, right? That's the very first step, and the next step is to figure out the unknown nodal voltages. So potentially I can see there are 3 unknown nodal voltages. So these are the unknown. So this one we don't know, right? What's the voltage here? We don't know. What's the voltage here? We don't know. And what's the voltage here? So these are all right at same voltage. All this color, right, with the green color are at the same voltage. So there are 3 unknown. There are 3 unknown nodal voltages. Actually, there are 4 unknown, but we just made one as 0 voltage. So that's the main advantage of using nodal analysis. So you can reduce one unknown variable using a nodal analysis, right? Okay, is this unknown node? No, because this is at 100 volts, right, relative to this ground. So this is not the unknown nodal voltage. So this is at 100 volts relative to this ground, right? So this is at 100 volts. So this, let's call the voltage here is V1. Let's call voltage here is V2. Let's call the voltage here is V. So you basically have 3 unknown nodal voltages, and our job is to figure out these 3 unknown variables. So, and then algebraically, if you have 3 unknown, right, you need 3 equations. So it's a 3 unknown, 3 equations problem, right? And solving. So and remember, this is a current source. It's a constant. It's a current source. It's delivering a constant 8 amps of current in this direction. It's a current source. And this is a voltage source, obviously. And it's delivering constant 100 volts. So let's get started. So I'm going to apply KCL, Kirchhoff's voltage law, at V1. Right. So we're going to apply Kirchhoff's voltage law at V1, V2, and V3, and we'll be solving 3 equations. That's it. So at V1, apply KCL, Kirchhoff's current law. So let's see. And the direction of the current is also not given to you. So, and you can, if the direction of the current is not given, you can choose your own direction of current, right? And that's not a big deal. So if the direction of the current you choose is wrong, you will end up with negative current, right, or negative voltage at the end. And that's the main beauty of using Kirchhoff's laws. Okay, let's choose. Let's do the educated guess of the currents. Let's say this is I1. Let's call this is I2. Current here is Ix. Let's call this current as I3, right? And let's call this as I4, and finally I5. Current here is 8 ohms. So these are the currents, right? But in this problem, it's not asking all these currents. It's just asking this current. Okay, so if you choose this current in this direction, this side is positive, this side is negative, positive, negative, positive, negative, and that's your next step, choosing the polarities based on the current that you have chosen. Okay, at V1, then what would be the KCL? So I1 must be equal to I2, right? plus Ix, right? And let's now convert into the nodal voltages. So I1 is 100 minus V1 divided by 8 ohms is equal to I2 is what? V1 divided by 4 ohms, right? Plus Ix is V1 minus V2 divided by 2 ohms. So that's the Kirchhoff's law at V1, right? And so now play with this, simplify this equation, you'll get one first equation, and I'm just going to write down the equation. I have already solved it for V2 plus, so there's no V3 here, so you can just make the coefficients as V3, because I'm going to tell you why we're including V3 as well. So since there's no V3 in this equation, you can just make the coefficient of V3 at 0, but you can still include V1, V2, V3. Okay, this is your equation number 1. Now you need 2 more equations to solve this problem, right? So now do the same thing. At V2, what is the KCL at V2? Same thing. So Ix is equal to I3, right? No, there's 8 amps current coming as well. So at V2, Ix is coming plus 8 amps is coming, right? Because of this current source, 8 amps is coming. And I3 is going out of the junction. I4 is going out of the junction, right? Is equal to I3 plus I4, right? But Ix is V1 minus V2 divided by 2 ohms plus 8 is equal to, what is I3? So I3 is V2 divided by 3 ohms plus, what is I4? So I4 is V2 minus V3 divided by 10 ohms, right? And once you have all this, now you can just simplify that and get another equation. So I'm just going to write down the equation, simplified equation. So this is your second equation, right, in terms of V1, V2, and V3. So you can simplify your own way, right? So this is, I'm calling this equation number 2. Now you need one more equation. So I'm going to use Kirchhoff's current law at the junction V3, at node V3, right? And do the same thing at V3. Let's see, V3, what's going in and what's going out. So I4 is coming, right? 8 amps is going out of the junction. I5 is also going out of the junction. So I4 is 8 amps plus I5 is also going out of the junction. So what is I4? So I4 is V2 minus V3, right? V2 minus V3 divided by, what is the resistance? 10 amps. 8 amps plus, what is I5? So I5 is V3 divided by, V3 minus 0 is V3 divided by 5 ohms. Okay, again, simplify that. So once you simplify that, so there's no V1 here, so you just make the coefficient V1 plus V2 minus 3V3 is going to equal to 80. Equation number 3, right? Now since you have 3 unknown, 3 equations, and you can solve that, right, in many different ways, and one of the very effective and very easy way to solve 3 unknowns, or if you have more than 3 unknown variable, is to put them in matrix form, right? These are all linear equations, and they can be written in terms of 3 linear equations in terms of matrix, and then just solve it using either a calculator or or any computer program. So I'm going to show you how to write down all these equations, right? So just keep that in mind. So I have this, all these equations, right? Now I'm now going to put them in a matrix form. Remember all these three equations, right? Now all these three linear equations can be written in this nice matrix form. And why do you need that? So so this is your first coefficients, right? So 7, -4, 0, -15, 28, -3, and 0, 1, -3. And here goes the unknown variables, right? And on the right hand side you have 100. This is from equation number 1, 2, and 3, right? So those three equations, right, three linear equations that we just solved, can be written in this matrix form. Because if you solve this matrix, right, if you open this matrix, right, if you open this matrix, you're going to get those three equations, right? All those three equations that we just solved, I just showed you, can be written in this form, right? This plus this is this, right? So this is a three linear equations, right? And then this is the unknown. So then V1, V2, V3, which are the unknown voltages that we're going to solve, is going to be 7, -4, 0, this 3×3 matrix, right? 3×3 matrix. This is the inverse of this 3×3 matrix times the right hand side, right? 3×1 matrix. And now you can solve this equation using your TI-84 plus calculator or any other calculator that supports the matrix algebra. Or I'm gonna show you how to solve this matrix using Python programming, using NumPy package. Okay. All right. Now I'm going to show you how to calculate that 3×3 matrix to solve the unknown voltages V1 and V2 using Python programming. And it's very easy to solve that matrix, to solve the unknown voltages using Python programming. You just need to import a package called NumPy. And you can solve the same 3×3 equations or any unknown variable using TI-84 plus calculator or any calculator these days, right? But it is very convenient to use Python programming but make sure to learn how to use a calculator to solve those linear equations. So I'm using a Jupyter notebook. It comes with an Anaconda package. If you have downloaded an Anaconda package, you can automatically run this Jupyter notebook. So first, your job is to import the necessary package. So import NumPy as np, right? So that's the package, that's the only package I need, NumPy. And NumPy is a very useful and very famous package to do all the numerical calculations in math and physics. Okay, now you have to put the matrix in this format. Let's say A is A, right, times X is B. You have a matrix equation, that three equations in this format. Now your job is to find this unknown variable matrix, 3×1 matrix X is going to be what? A inverse matrix of A times B. That's what we're going to do, right? Inverse matrix of A times B, right? And then, so let's comment that out. So I have to put that in this format. So first I'm gonna define my 3×3 matrix A, which is you have to put in NumPy array, right? You have to put in like this in this format. So you have a 3×3 matrix. So you are making a list of list and list of list, like that, and putting all these codes. So from first equation, your coefficients are 7, negative 4, 0. From your second equation, your coefficients were negative 15. If you go back to that equation and see those coefficients, and this is just, I'm just putting in matrix form, and 0, 1, negative 3, right? Okay, so that's my 3 by 3 matrix A, let's say. And now I have to define a second matrix, which is B, which is the right hand side, right? So np.array, we just need our list, and those are 100, right, from 3 equations, the right hand side of the equation, 240 and 80. So that's my B, let's say, right? Now you have to, X is going to be in, so you have to now use a method or object called linear algebra. In that numpy package, you will see this linear algebra method, right? And it takes that to first, and within that linear algebra method, we are going to first use the inverse function, right? Inverse method, right, of linear algebra. And inverse of what? You have to do the inverse of, you have to first make the matrix A inverse, yeah. And then your final, let's say C is, this is what we want. No, I'm sorry. Let's call this something A inverse variable, right? I'm going to call this A inverse, and C, and then our unknown variable X matrix, that's what we want, is going to numpy, and we're going to take the dot product between the inverse matrix that we have just done and B, right, based on this. So based on this, right, based on this. And that's all. And let's see what X contains, right? So now that's it. This is our answer. So your the unknown. So this is it outputs a list of 3 unknown elements, right? So this is your V1. This is the first unknown voltage. This is the second unknown voltage, and third unknown voltage, right? So that's, you can use this line of codes, few line of codes to solve the matrix, to solve the unknown voltages, right? And you can just extract those elements in that if you want. So for I in X, right, you can extract those, right? So these are your, this is your, I'm sorry, in X. So that's your answer, right? So I'm gonna show you one more method, or you can simply use without, if you don't want to do inverse matrix, you can directly solve this problem by just by doing this X. You have A, just by using A and B arrays, X is going to be numpy and linear algebra method in linear algebra ALG, and you have to use within that linear algebra, just use solve method, right? Solve of A and B, right? And that's it, and that's going to give you the same answer, right? See. All right. So now, as we already know all this unknown variable, right? And these are the results, right? So V1 was 25.9 volts. V2 is 20.3, rounded, right, to 3 CP. V3 is 19.9 volt, right, and negative. So we got negative, right? So we got negative V3 as negative voltage. So that means that, what does it mean? So V3 turned out to be negative 19.9 volt. That simply means the direction of the current I5 is not this way, right? The actual direction of the current is upward, right? From here to here. That's the meaning of V3 as negative 19.9 volt. Okay, and that's fine. So if you choose the wrong direction of the current, right, you're still fine. You'll end up with negative current or negative voltage. Okay, so these are the unknown voltages that it wants us to solve. There's one more question on this. So what is IX? What is IX? IX is here, right? IX is the current through 2 ohm resistor, and you can find out very easily because we already know this nodal voltage is V1 and V2, and IX is just V1 minus V2 divided by the resistance 2 ohm, right? So I of X is just V1 minus V2 divided by what is the resistance 2 ohm, right? So V1 is 25.9 and 20.3 divided by the 2 ohm resistance. So I of X is going to be 2.8 amps. Okay, so that's how you can use the nodal analysis technique, right, to solve the complex network, complex circuit problem, right, using the Kirchhoff's current law.